All right, so let's start out with just a little bit of review first so you remember where we left off, right? So we talked about gates and what they mean and the truth tables, the logical operations that they perform, right? So this here with my wonderful drawing is an inverter, right? So it just takes whatever the input is and does the opposite. So if it's a 0, output is 1. This symbol is an OR gate, right? So if either of the inputs is true and if both are true, or sorry, if either or both are true, the output is 1. AND gate, both inputs must be true for the output to be 1, right? So those are our main symbols. We can then redraw those into NANDs and NORs, which we'll get to with this example. We also talked about Boolean algebra, and I'm going to go through some examples so we can see that, because the Boolean algebra tends to get people stuck and confused. And both of these have something in common. What theorem are we going to have to use to simplify these? De Morgan's theorem, right? Because you have many terms underneath a not bar. Remembering that I can write not, so if I want not x, is that or that? Right, those are equal. Okay, so let's just start off with this example of De Morgan's and go through and simplify it, and then I'll have you guys attempt to do this one on your own. Okay, so this portion of the equation, right? So this is going to be something like f is equal to that, right? This isn't really problematic. That's an easy OR gate to draw out, right? Plus sign is OR, multiplication, whether implied or explicit, is AND gate. Now, De Morgan states that we're going to flip ANDs to ORs and ORs to ANDs, and we're going to invert the terms. Now, in this case, the terms aren't A and B and this and that, right? This is one term of our De Morgan's, that's the other term of our De Morgan's. So when we do it, this OR becomes an and then we have AB bar bar, A bar B bar. Right, I'm not flipping the individual A's and B's yet. But now I'm going to do it again. I'm going to do De Morgan's again on both of those. And now I get to put bars on both of them. I'll add parentheses to make it clear. What does bar bar mean? No bar. They cancel. Not, double negative, goes away. We can do that same thing over here. It's still an AND. Don't flip this one, right? Because it's not under a shared bar. I have A bar bar or B bar. And then we can bring this guy down. If we were to stop here, well, okay, so we can pull this out, right? Bar bar again goes away. We have a term for this, a name for this way of expressing things. What do we call this? Sum of, well, no, this is a product of sums. Yeah, so it's the product of sums. So I have several sums that are multiplied together, product of sums. Okay, but this is not as simple as it can go, right? It's unlikely in the case that I only have two terms that I'm going to need this. It's possible, but unlikely. So what we can do is we can either start looking for ANDed terms that could cancel, or we can start factoring them out, multiplying them through to try and find something. So I don't really see anything that jumps out that we can cancel straight away, right? If we had another A or B without any of the other terms knotted, we could probably just simplify, cancel that out, but we don't. So I have to start factoring, or multiplying through, sorry. So I'm just gonna pick arbitrarily these two to multiply through. So we can FOIL, or we can do what we kind of talked about last time and kind of separate them out. What I'm just gonna do and go ahead and FOIL it. So A bar, A, first outside I'll just leave that one floating there for the moment. Now, there's kind of a good reason that I chose these two, and it's because they both have barred terms and they're different. So if you see that, you can kind of suspect that maybe you'll get some cancellations, right? Because you have a bar and a not bar, and they'll cancel. Example, what is A bar and A? Zero. It can never be true. So that one goes away. Well, that stays zero. Okay, cool, nice cancellations, right? Now we just have two terms and two terms, and we could multiply it out again, unless you see something that we could cancel. I don't. One way, let's not forget our tools, right? If we wanted to, we can draw the truth table for this expression. And if you're stuck on something and you're like, maybe I can cancel it, what is sometimes good to do is just draw the truth table. So if you recall the truth table, A, B, and this is the expression B, right? I know I have 2 to the n rows, or 2 to the 2 rows, so 4 rows. If I have not A and not B, it's true. Or I have A and B, it's true. Does this look like any of the gates that we've used before?
Like a not exclusive or.
Yeah, it's kind of a weird one. We don't have to worry about simplifying that, right? We're good. That's not like another gate hiding in there that's easy to use. Okay, let's do some multiplying through then. A bar, B bar, or B bar, B, or A, B, or, sorry, I did that one wrong, didn't I? No, that's right. A, B, A, B, B. Is that right? Feel free to check my work. I'm not immune to errors. Sound good? Everyone sees how that's happening? Okay. Now, again, this is a 3-input AND gate, but can I ever have A and not B? Can this gate ever be true? No, goes away. Same problem, right? B bar and B can't happen. So in a 3-input AND gate, I need all 3 to be true in order for it to be output true. Can't happen, goes away. Now, this A and B, do I really need 3 inputs there? What is A and A? It's just A. So that's AB, or what's this term? AB. What's the next simplification? Yeah, we can just drop one of these, right? This or that, but they're the same, so who cares what the other one is? AB. This expression is equal to and B. Now you could go through and you could draw out a whole truth table for this and prove it, but that would be kind of tedious. Okay, so go ahead and start doing this one on your own, because you want to work through it to make sure you're following along and not just making the assumption that it makes sense to you, because De Morgan's is kind of tricky. If you just Google, this is all I did to find these examples, just De Morgan's examples, they'll pop up. The common issue that students have. Anyone still working on this? Okay, so do this one right. Did everyone get that? Did I do this one right? And did everyone get that? Okay. From here, what should I target for further simplification? They don't see something that I can try and simplify. Yeah, exactly. So these are all just ANDed together anyways. So I can just reorganize them however I want, right? It's multiplication. The order of multiplication doesn't matter. So I can clarify that this is so this can be true because it's repetitive. This is fine, but repetitive. And then the C just comes down. These parentheses aren't really necessary, right? Because they're all pluses, so I can erase them, make them easy. We have a common term in all of these, right? We can just pull that whole A bar out. 1 or B, right? So A bar is out. So it's 1 or B, or, well, let's just say this. Does the rest of this matter?
You have a 1 on.
I have a 1. 1 or anything is always true. Now I can pull it out, right? I can finish through. This is essentially 1 C bar or BC. But that 1 in a series of ORs, now 1 is always true. If there's 1, 1 on an OR, it's always true. Does everyone see that?
I just don't see how you can factor the A out, because it's with, like, when you factor the A back in, you get A not B.
Yeah, say the B
Oh,
should be outside the parentheses.
that's a good point.
You can't pull the A out.
You can out of the 3, just the B has to be outside of the parentheses.
Say that one more time.
The B has to be at the outside of the parentheses.
But that doesn't
Oh,
work
the
either,
B,
because
I
you have an
see.
A, B
Oh,
term.
yeah, so the B is the issue. Okay, so let's do that way. B or,
And then you can factor the end of the A term.
yeah, and then we end up with 1 or stuff. Thank you. Yeah, if it looks confusing, call it out.
Because it would have to be true when B is true.
Yeah, okay, so now we have A and 1. So this expression can go away, and we have A, not A or B. That sounds right. This one. Yeah, don't be afraid to call it out. I am. Okay, so that's the Morgans. You'll be almost certainly expected to answer something like that on an exam. This book doesn't spend as much time as some others on the Boolean algebra, so I'm just kind of enforcing this as much as I can so you can follow along, because the Boolean algebra really underscores a lot of what we do. And then we'll have some other tools to simplify this process later. Okay, so I'm going to bounce over to, let me point the camera in the right direction. This circuit. So I mentioned last time that we may be in a situation where we want to use NANDs or NOR gates instead of AND or OR gates. And we're actually going to figure out, see why. We're going to see the circuits that build these this week, today or Thursday. One of those two will see it. But for now, what we want to know is the process by which we do that conversion. Now, it's easy, and I will rarely ask you to do it outside of like a sum of product or product of sums situation, but this is, what kind of expression is this? Is sum of product or product of sums? So we have an AND gate at the output, which makes it a product of sums. The sums come from the OR gates. The product comes from the AND gate, right? So this output here is X or Y. And this tool of writing out and labeling what your wires are, what your nets are, is really helpful so they don't get lost in what you're trying to do. Right, so Z becomes Z bar here after the inverter. And then this is Y or Z bar. which means my F is equal to, going up the screen, I'm gonna come down here, F is equal to Y or Z bar and X or Y. So that's how I take a circuit and turn it into an expression. Label the nets, fill out the expression. Now, if I want to do this conversion, what I do, I always just call the term bubble pushing. I'm sure it has a proper name or something. You'll see different ways of doing it, and I always recommend this one. So this is a right to left methodology where I have the AND gate, and I'm going to turn it into a NOR gate because NOR is one of our universal gates. It's a NOR gate just by doing those two bubbles. Because a NOR gate is equivalent to that. Okay, but I've just ruined this net and I fix it by pushing another bubble here. Right, because if I do not, it's equivalent. I haven't changed anything. But I've changed the type of gate that I'm using. Now this inverter, if I want to just use a NOR gate, I can use a NOR gate as an inverter. How would I do it? How do I wire up the NOR gate?
Just cross the inputs.
Does everyone see that? What is this truth table? Well, NOR, what's the truth table for NOR?
We don't care about the two ones in the middle, because this never happened. We don't care about the 0, 1 or 1, 0, right? Those are just, we don't care terms.
Well, kind of, yes.
Because once we cross the gates, that's never gonna happen.
Yeah. So this, I want to start off with the NOR gate so that we can follow through. Yeah, but you're right. Because this can't happen, right? Those are impossible if A equals B. So the only rows that matter are are row 0 and row 3, right? Because those are the rows where their A and B are equal. So then, if their 0 is 1, if the input is 1, it's 0. That configuration for a NOR gate is equivalent to an inverter. Okay, so take a moment, use this one. It's going to be a little bit different, and you're going to have to add at least one gate for this, and you'll find out why. So start from right to left and go for NAND gates. If the output ends up being an OR gate, you're doing a NAND gate design. So what I do, right, NAND gate is add some bubbles, and I may have been wrong on this one actually about needing the inverter, but I'll find out. And then I just push, right, so conceptually what I'm doing is I'm saying there's two bubbles right here. This is why I call it bubble pushing, is because I'm undoing each of them. And then I just take this other bubble and push it all the way back until it hits these guys. So now that's a NAND gate. Those are NAND gates. This is not. So it turns out I'm actually wrong. I don't need it, do I? I don't need the extra inverter. Because to make that a NAND gate, it's just the same as this one. And then oh yeah, I do need one inverter. So now this has a second bubble that needs to get pushed, but there's no gate to hit. So here I make the gate. And then I push that bubble into the buffer, right? So remembering a buffer, the output equals the input. And if I stick a bubble on the end of it, it's an inverter. Unless I explicitly say otherwise, I will say if you're not allowed to use inverters. In general, just assume that you can use an inverter. If I say no inverters, then you have to convert the inverter to a NAND gate as well. Make sense? But generally, I will let you just use inverters because it's not hard. Just go like we saw, right? Okay, does that make sense, everyone? Good. Okay. We're going to go ahead and do a design problem. So this is going to be on page 52 of the book, I believe. Yep. So we're going to do two different design problems. These just basically mean story problems, everybody's favorite, right? We kind of talked about this concept last time, but we're going to increase the complexity. So the example that we're going to use is the light switch. So let's say that you have a room, say it's your living room. It has 3 different entrances, and each entrance has its own switch. Now, when you start, they're all down, they're all off, right? So we're gonna, for the switches, we're gonna say if it's up, the switch is on, and this is always a little bit confusing because you can have the circuit being on and each switch being on or not, right? So, on, off for the switches, right, the light switch. But that doesn't necessarily reflect what's going on with the light, right? So if I walk in the front door and I flick on the light switch, they're all in the lowered position, the light's off. I come home, I flick on the light switch, it turns on. I walk to the other side of the room, and I flick that light switch, it turns back off, right? So now 2 are up. If I walk to the other one and I flick it up, the light goes back on. So what we want to do is write an equation that expresses when the light is on in terms of the switches. So let's call the switches X, Y, and Z. 3 switches. And we're going to write a function, F, that represents when this light turns on. So we know it's not on if they're all down, right? That's what we established. Well, when we walk through it, it is on when, let's see, what are the conditions exactly? What are the conditions that turns on someone? Give me one part. So I'm going to write this as a sum of products. Give me one sum that it is true on. 1 switches up, right? So what does that mean? Well, we know that all of them are going to have this expression in them because they have 3 variables. And if 1 switches up, it could be X, it could be Y, or it could be Z. Let everyone see that? Okay. And the last one is I detailed is they're all up. Basically, it's saying if there's an odd number of switches in the up position, on position, the light is on. Now, just recalling if this was an expression of min terms, remember how we did that? I could also say, and you may need to draw out this truth table to see this, but it's a sum of 1, 3, 5, and not 5, 4. 1, 3, 4, and 7. Nope. Sorry, the zero indexing confuses me sometimes. You just draw out the truth table and see which rows corresponded to each of these elements of the expression. I just want you to remember that min terms is a thing. We're not going to use too much with that. So we have this expression. I need a circuit to make it, right? So someone came to you and explains the design to you. You come up with this expression, let's make the circuit. Where do I want to start with this circuit? Where's a good place to start? It's a sum of products. What is the output gate? An OR gate, yes. How many inputs does this OR gate need? 4 inputs. What is driving each of those 4 inputs? What kind of gate? 3 input AND gates. And gotta fire this guy. Okay, and then you could go through, there's a couple different ways to do this. You're welcome to whichever way you want. You could just go through and say X, Y bar, Z, and so on. That way doesn't really work for my small drawings. So the other way to do it is just over here, right? X, Y, and Z. And then you can throw the inverters wherever you need, right? So X goes directly in here and then has an inverter down to there. And here, and out there. And I could go and fill that out. I don't have much of a preference. I actually kind of recommend not doing it this way unless I tell you to, just because you can see how messy this can get real quick. If you have nice, orderly handwriting and are better drawing than I am, then this way works much better. I'm a terrible drawer, so this doesn't work very well for me. Okay. We have our circuit. We just went through how we would turn that into NOR gates, right? Or sorry, NAND gates, really easy. Right, just start pushing some bubbles. One step, nice and easy. Okay, easy design example. Let's move on to a little bit of a harder one. If I ever say something is easy and it's not, call me out on it, because you know professors should do that sometimes. But hopefully that one is easy. So what we're going to talk about next is an important circuit, very important circuit that you're going to be using in your designs all the time in this, well, the second half of the semester. The circuit is called a multiplexer or a mux, M-U-X, multiplexer or mux. So what a multiplexer is it has this circuit schematic. Okay. We call this a mux or a multiplexer. So what this circuit does is it has S, a select signal, that chooses F to be either A or B. So it's changing the path. It's selecting one. This truth table then, we have 3 inputs. How many rows am I going to need? 8 rows, 2 to the 3. Oh, wait. Okay. Truth tables are nice, useful tools for us, right? So, when select is 0, right, it's just a binary input, meaning 0 or 1. When select, S, is 0, we take A. So in this case, A right? Select is 0, choose A. Therefore, the truth table, the output, just mirrors A, the input. Then select is now 1 down here. So when it select is 1, we're choosing B, so follow B. Then we can write the expression from this truth table, right? So we're starting to see, we're going to do a whole lot of make the truth table, turn it into a circuit, build a circuit, turn it into a truth table, and the Boolean algebra is throughout all of this, right? We're starting to see how all of this kind of is back and forth related. Okay, so now I just take the min terms, right, or expression, and write them out. So this min term, if we recall, actually take a moment, write the min term for me. The 4 min terms, actually. Right, and then I just string the min terms together with ors. Did I get those right? Did you guys get those right? Okay, and now that we have an equation, we know how to simplify this. Well, hopefully we do. We can start looking for terms that we can simplify. Now, sometimes there will be simplifications that will end up not in a sum of products expression. So sometimes what I'll tell you to do is use the simplest, find the simplest sum of products expression. Other times I'll tell you to find the simplest expression. Does everyone understand the difference between these two? Okay. I like to start looking for things to pull out, right? S bar, SS, maybe we can do something with that. That look like something we have. It's I think I have a. Do you want to remember what page those? There we go. It's on page 33, and it's. Oh shoot! It's not quite right, is it? Might not work.
You can plug the A as well.
Ah, good call. So we can pull out an A and have an S bar A, B bar or B, which is always 1. So we have S bar A. Good call. Here, same, yes, excellent. Yep. So I'll just drop this all the way down here. SB times A bar or A. Goes away. We end up with S bar A or SB. Well, that's a pretty nice, easy circuit. I could actually do something probably if I was using XOR gates, but let's just leave it at ands and ors for now. Now I have an output OR gate. I have two input AND gates. S bar A, S B. So that essentially is what's going on inside of this guy. Now, this, right, output OR gate means it's easy to turn into NAND gates. At some point, I will probably go back and have you do a homework with some explanation of using the max terms instead of the min terms, because max terms make it easy, give you an output AND gate, which means it's easy to turn into NOR logic instead of NAND logic.
I have a little off-topic question. In CMOS, isn't it NAND gates are easier to build, and then in TTL, it's what? One of them's like easier to build and like
Yes.
less transistors than it.
Yes,
is the least.
exactly. And we will get into exactly what those transistors look like. And that's why that's why I keep talking about the NAND and NOR gates, is because they're prolific in use because they take fewer gates to design than AND and OR gates. So like in CMOS, which we'll get to today, I think, it'll make more sense to all of you. He's jumping a little bit ahead once we kind of walk through this design flow. I won't skip too far ahead so we don't confuse people. Okay, so you've seen now 2 design examples. So I can ask you questions. Go design for me and then describe something to you. Understand that your first goal is to identify some sort of expression that you can use, simplify, and then draw the circuit. So I might, for example, a good question is instead of a mux, I would say something like, design a circuit that detects when an odd, or say an even number of switches are on, right? Very similar to the other one. We have the prime number example, that kind of thing, where we're going to draw an expression, simplify it, draw a circuit. That's your design process for now. It'll get a little more complicated as we go along. The book likes to point out, and you'll probably see this again, an alternative truth table for this.
Where only one changes, right?
Yeah, so we can draw just for S. Right, so if S is 0, we take A. If S is 1, we take B. You'll see some like this, where instead of drawing the function is just determined by a variable. I won't do that expression very much, but I want you to be aware of it because it does show up in the book.
I just have a question. I've seen sometimes where they like write truth tables where only like one bit changes at a time. So they like
Yes.
reorder the.
Yeah. I have that scheduled for a little later. It's called gray code. Okay, so we're switching modes a little bit. We're now jumping into chapter 3. So chapter 3 is we're going to talk about how these gates are made. So what we need to know is that there is something called transistors. There are two main types. There is that we're concerned with. There's more than that, but there's two that we're concerned with. One of them is an NMOS. One of them is a PMOS. And if you design a circuit that uses both of them, you get CMOS. C in this case stands for complementary. Now, as you move through this program, you will learn a lot about these devices. For now, what you need to know is I can draw an NMOS, and there are actually many ways to draw this, like so. A PMOS looks very similar, but it has a bubble, much like the inversion bubbles. I'll leave them separate for now. That we saw before. So, let me space these out a little bit so I don't confuse when I draw this. In the case of an NMOS, if I label this node A and this node B, and I'll use S for now because we're familiar with the term select. What this does is make a switch that closes when S is high. So if S is 1 or high, the switch closes and it carries through. A and B are connected. A, B. If S is low, the switch is open and A and B are not connected. A PMOS is just the opposite of that. If S is low, 0, it's closed, and A and B are connected. If it goes high, it opens. Another term for that, normally opened. So if there's nothing going to it, a 0, it's open. PMOS is normally closed. If there's a 0 going to it, it's closed. Closed means connected. I'll call them out for the NMOS. So what we really call A is the source and B is the drain. I'm not going to be using a lot of that terminology. I'll save that for your circuits courses. Mostly just focus on understanding that these are working like switches for us with this kind of behavior. But don't let it skip your head that this is not a given. They can behave other ways. So when you get to other classes, don't be like, but it was a switch, because they can change. We will always operate them as other switches. Sometimes you'll see this symbol added to them. It's the same symbol. It just means something a little bit different. You could also see it like that, still the same symbol. There's about a dozen different ways to draw each of these. I will stick to the first ones that I drew up. I think the book does too, so we're in luck. All right, so if you recall, first day I drew something like this. This is a little bit different and really ugly because I can't draw. Okay, so this is a resistor, remember? This is now an NMOS transistor with a select signal. And then I'll do something like call this VX, the output voltage. Okay, so S is my input, V is my output. I have a supply here, right? It's creating a voltage. I will usually provide a ground for you, somewhere they call 0 volts. But what you need to understand is this is a 5-volt battery or a 5-volt supply. Then from this side of the battery to that side of the battery is 5 volts, right? In this case, I'll say 5 volts is on. So my digital logic may use some voltage for on. Common voltages for on, 5 volts, 3.3 volts, 1.8 volts, 1.2 volts. Those are your most common on voltages. Okay, so this is a switch. If it's 0, it's open. Therefore, current can't flow if there's nowhere to go, right? So electricity is like current. So if this is an open switch, there's voltage here, there's supply of water, but there's nowhere for it to go, no current flows. Therefore, this node is the same as this node. Okay, let me draw this real quick. Open switch, right? 5 volts just sits and hang out here. The voltage drop over the resistor, the Ohm's law, is V equals IR. If current is 0, the voltage drop is 0. The current has to be 0 if there's nowhere for it to flow. Therefore, Vx is the same as 5 volts, therefore on. So if your input S is 0, your output is 1. Okay, so let's say I turn it on. I put 1 onto this S. It closes. Now your voltage drop, well, we could go through a whole bunch of Ohm's law stuff for this, or I could just point out, you have voltage up here at 5 volts, blocked by a resistor, and here we have ground at 0 volts with no resistor. Ground with no resistor will always win. So it just becomes 0. Now, that's kind of the intuitive level for it. Now I'll show the Ohm's law for it. So another part of circuits, sometimes I forget how hard this can be explained to people that haven't taken any circuits classes, so I want to make sure everyone follows along. But this is kind of intuitive, fortunately. If I start at ground here and I go around the circuit, I have to end up back at ground, right? So in the circuit, if there's a resistor, that resistor, essentially, what that means is that has to take the same amount of voltage as the supply. So we go up 5 volts here, and we lose 5 volts over that resistor. If I had 2 resistors, I can't, if I don't know the values of these resistors, I can't say how much voltage is there. But what I can still say is over those 2 resistors, I must lose 5 volts. If someone here hasn't taken or isn't taking 1270, feel free to schedule some time in my office hours if you're confused on the Ohm's law part. I know it can get confusing for some people. It's one of the things that people hate, and just the circuit node equations. I'm trying to keep the circuit part simple because it's not what's important, and we'll very rarely use more than one resistor in this class. Okay, but what we want to do is we're going to lose 5 volts over that. When this closes, current flows, it drops. We end up with zero on the output because it's closed, it pulls it to ground, right? It looks like this. So if you draw it out, it's pretty obvious when it's drawn out explicitly that this node Vx is directly tied to 0 volts and is therefore 0 off. Don't be afraid of redrawing circuits like this in order to make sure it's kind of clear to you what's happening. So, in conclusion, this circuit with an NMOS, if I have this guy, what is that? What function is it performing? It's an inverter, right? Input is 0, output is 1. Input is 1, output is 0. This here is an inverter. Sometimes you will see an inverter, right? So this is our standard symbol of the inverter. If I want to be more explicit on it, I say it's powered from ground to, well, I'll use the symbol VCC. So this symbol is now showing that what my supplies are. So I could say that this is 5 volts, for example. Okay, this is a slightly different way to draw essentially the same thing. So this VCC, so this line with a bar across the top, that's a supply or a rail, right? We talked a little bit about that. That's the same as just, I'm replacing this part of the circuit with VCC. So there's a voltage somewhere that is providing it to this node, and it can drop to ground. Now, knowing that A and B are both NMOS styled switches, what is this circuit doing? And again, truth tables are your friend. Okay, if they're both 0, both off A and B, what are the switches doing?
blocking the current from going to ground.
Yeah, there's no current flowing. So what is Vx? 1. It's high because it can't get to ground, so it can't be 0. It's high. Remember that you can draw it like an open switch. Broken, right? Current can't go anywhere, so it's pulled high. We call this resistor a pull-up resistor. You will see me write it occasionally as RPU, R pull-up. What it's doing is if there's not something stronger pulling it down, it's pulling it up to on. Well, these switches, they override, they win that resistor because they have no resistance. So they're able just to sink a bunch of current, is what we say, pulls it to 0. But they're both broken. Okay, let's say that A is still 0, but I close B. What happens? Still nothing. So what is the value? 1. Same holds true here, right? It doesn't matter which of those switches is closed. But if they're both closed, now we'll be able to pull it to 0. What kind of gate is this? NAND gate.
So for an NMOS, 0 is open or 0 closed?
0 is open.
Okay.
So I've drawn the normal situation, which means here, which is what it's doing when 0.
And it's NMOS because it's like an N-type semiconductor in the gate. So it
Yes.
pulls electrons in and then it can flow.
Yeah. So you guys will get to device physics later in the program that talks about why this is true. But basically what's happening is that if you have electrons on one side of the transistor and we'll just say a voltage differential, right? More electrons on one side than the other. They're trying to get to each other, but there's no path there. And what this applying a voltage here does is it lowers a barrier and allows them to flow through. That's a very simplified version of it. We don't.
But with CMOS, there's almost no current going from the switch to the gate.
Yes, with an NMOS, there is almost no current that flows from A to B. So, the current flows freely. Sorry, that could be confusing because of my labeling. I'll go here. Current flows freely from A to B if it's asserted, but almost no current flows from S to B or S to A. Very, very small amounts. And in fact, in this class, you'll just assume it is 0. Later on, you'll deal with some of that, but that's actually like junior level stuff. So, I don't know. Okay, so let's go ahead and build an a NOR gate. About that. Okay, so the NOR gate is going to function very similarly. We're going to have a pull-up resistor. But what we need is something a little bit different, right? We need to be able to have the switches connect ground to our output. I already said this is a NOR, so if either one of them. What that means is we'll just put them in parallel, right? Remember the vocabulary? These guys are in series. We're going to put 2 gates in parallel instead. Right, so now if either A or B or both are switched on, closed, it goes to ground. Remembering that our truth table for the NOR gate okay, so let's take a moment and think. We've used 3 input AND gates multiple times. How would I add a third input to this one?
Another one in series.
Yes, and just add C in series. Right? If I had a third input, A, B, and C, then I would need all 3 to be on in order for the current to flow and therefore go to 0. If I want to add a 3 input or NOR gate, how do I do it? What do I do?
Same thing, but in parallel.
Yep, just another one in parallel. That way, if A or B or C is on, then the current can flow.
Is NAND preferred because like there's less times that there's current flowing, so it like uses less power?
Not really, because you don't know that really. And a lot of what matters is
A lot of the time could be spent at A and B, like it just.
yes. You could where you actually lose a lot of power in these ones is when they switch, when they change.
There's a lot of potential in the
Yeah.
gate, so.
Yeah, so they're sitting there kind of flowing. But that's another reason we like CMOS, which I will make sure we get to at least one of those shortly. Because CMOS current doesn't flow hardly at all, except for when it changes. So you're right in that if we spend a lot of time at the and, we're consuming power all the time. But in CMOS, so let's go ahead.
But we can assume that like that resistor is fairly large compared to,
Yes.
because we don't need, because that presumably that X will go into another CMOS gate and we won't really need like any current, just enough to fill the gate.
Yeah. So what he's getting at is this resistor has to be large in order for this to work. You're going to build circuits like this in lab next week. And if you make it too large, it can be a problem. And we'll kind of talk about that in lab. But we want to build a CMOS device. And we'll get to, we'll start with this CMOS inverter. So the issue that, sorry, what's your name? Ben is talking about is that if A and B are both on for a long time, potentially, right? Say this is like the normal situation. That means both of these are closed, and the whole time that they're closed, electricity is flowing, which means power is being consumed. It means you're paying for it. The same thing happens in the inverter. Anytime the inverter is closed, it's consuming power. So let's go look at a CMOS inverter. Yeah, I got some room. Okay. Okay, so now I'm using CMOS. complementary. I'm using NMOS and PMOS devices in order to build an inverter. Okay. So if A is high, A is 1, right? This closes. This switch stays open. Therefore, we pull it down to ground. So that's the 1 case. In a 1, this switch closes, pulls to ground. 0, this switch opens, this switch closes, pulls to VCC or on 1. But what you'll notice here is that in neither case are both switches closed. And so in neither case does any power get consumed, except for when you're changing from 0 to 1. So what we call that is, if it's just sitting there and consuming power, static power consumption. So if it can use power without changing, as is the case with this circuit, as static power consumption. If the power is only consumed when you switch from a 0 to 1, it's dynamic power consumption. The last part before I wrap up here that I'll point out, the other benefit to CMOS is it's faster. Much faster, in fact, because this resistor is large, right? So you can picture it like a small pipe. It has a hard time reacting to changing currents through it. This doesn't have those large resistors. It can react faster. So we like CMOS technology because it consumes less power and, sorry, it just left my brain. It consumes less power and is faster. So that's CMOS. We'll get into next time some of the CMOS AND gates and NAND, NOR, OR, and you'll see why we like NAND and NORs over AND and ORs because of the number of gates. Anyways, again, I have office hours sometime. It's posted on the syllabus. If you get confused, you can come bug me during office hours.
Just one question. Can you explain static and dynamic power again, just real quick?
Yes. So if A and B are both high, 1 and 1, then the current can flow from VCC to ground, right?
Yeah. And it's
So-
just-
it just sits there, right? So like you leave your switches on at home and it sits there, it just sits and consumes power that whole time. That's static power. Without changing the inputs, you're consuming power. Dynamic power, right? No current is flowing on this one. No matter what, no current from VCC to ground. Because one or the other one is always open, there's no connection there. Therefore, you only consume power when you change from 0 to 1. So it takes effort to do that, right?
Yeah.
That's dynamic power.
Okay.
So I'm changing and it takes work to do that. So this circuit will have both static and dynamic power. This one, as long as these devices are ideal, which they're not, but if they're ideal, it's only dynamic power.
Okay. That makes sense.
Oh, sorry.
Is the